What we're going to approach now is an absolute foundational bedrock topic, solving basic trigonometric equations. One of the primary goals of the course is to get each of us to where in November we're able to solve trigonometric equations. If you ask almost any calculus instructor, Calculus 1 instructor, what they wish their students knew. Sometimes when I'm teaching calculus, students will contact me beforehand and say, what can I look at to kind of make sure I'm ready to go for calculus? Calculus instructors across the board say it. I say it the same way. Look at your trigonometry. Every calculus instructor I've ever known wishes their students were better at trigonometry coming into Calculus 1. In particular, solving trigonometric equations. Every calculus instructor in the world, I'm guessing, wishes their students were better at this. Now, what we're going to do is look at the most basic type, and then as we go through the course, we will pick up more and more ideas, more and more topics, more and more complexity, and the equations we begin to address become more and more complex. But no matter how complicated the question we get, no matter how complicated the equation, what we will do, what we're going to be doing in November, and when November rolls around, you can look back and watch this video and you can see I'm saying it right now and you'll see, yep, he sure was right. We're going to take these larger equations and turn them into these kind of equations. You take these larger equations, break them down, break them down, break them down until you get one of these basic ones. If you do not know how to solve the basic equations, then you will not know how to solve any trigonometric equation, because all trig equations break down to one of these basic ones. It is absolutely pivotal. It is foundation. It's a cornerstone that you need to know how to solve these, and you need to know how to solve them very well. You need to know without having to hesitate or question yourself how to work these out. A key thing, nothing here involves a calculator. We'll consider those later on, but for now, nothing here involves a calculator. If you're using a calculator to do this, you might be getting a right answer now, but you will be regretting it later on. I'm telling you that's going to happen. You need to trust me. I know what's coming down the road at you. I know some of you have goals in mind beyond mathematics, and you need to be able to do this without a calculator. So, in order to solve these basic equations, what we're going to do is these no frills. A function is equal to a constant. I am going to use the variable t, tango. The textbook uses the variable s, as in Sierra. I will not use s because my s's and my 5's look so much alike. It's easy to get confused, even for me, much less for students. And so I'm going to use the variable t instead of the variable s, whereas the text does that. Okay, so we're asked to solve an equation in an interval. So we only solve the equation in this interval. So the only solutions we want are between pi over 2 and pi. Also, this tells us that we're solving in radians. If it's pi over 2 to pi, then we know we're solving in radians. The similar question would be, suppose we're going to solve from 90 to 180 degrees. If this were given, then you know you're solving in degrees. It's not guesswork. This must be given as part of the problem. If it's not given, well, it doesn't have to be. That's a much more challenging problem. For us, for now, it must be given. If it's not given, we'll consider that later on. For now, this must be given. If it's given as multiples of pi, you know you're solving in radians. Here you're solving in degrees. We're, in this case, solving in radians. Now, there are three things you need to know. If you know these three things, you're good to go. You need to know ASTC. You know when all the functions are positive. What is the signum? What is the positive, negative of all the functions and all the quadrants? You need to know the reference angles. You need to know what to use with reference angles. You need to know the reference angle families. You need to know that if I have a reference angle of pi over 3, and you need to know that if I take reference angle pi over 3, and if you are in quadrant 3, then you need to know what that angle is. That's 4 pi over 3. You need to know the reference angle families. If you do not know the reference angle families, then you need to stop the video, go back and find the reference angle families, and learn the reference angle families. There's nothing for it. There is nothing for it. You must know this concept and what it represents. You must know the reference angles and the reference angle families. And then you must know the basic values in quadrant 1. If you know the basic values in quadrant 1, you don't need the entire unit circle. You need quadrant 1 if you know these. All you need is a quadrant 1. So, what do we know these basic angles? We have 0 radians, pi over 6, pi over 4, pi over 3, and pi over 2. If you know those, for us, for now, that's going to be good enough. Now, we need to know the sine values, the cosine values, and the tangent values. Remember? We can list these as coordinates because the sine is the y-coordinate. With the unit circle, sine is the y-coordinate. So we're going to have another chance to review that. We know this is 1 comma 0, so I know sine of 0 is 0. And remember our little rule, square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2, that's 2 over 2, that's 1. And then cosine is backwards. 0, 1/2, root 2 over 2, root 3 over 2, and 1. So cosine is backwards. If you can do sine with our little memory device, everything else you can get. All right? Now, we're going to, so if we have those, we are good to go. We are ready to go. What we have is sine of t is equal to 1/2. Here is the procedure. Write this down. I would almost say tattoo this somewhere on your body, but don't do that. That would be silly. You need to have this structure all the time, every stinking time. We will do quadrant check, reference angle. And I will abbreviate reference angle, reference angle. I'm going to do quadrant check, QUAD. I'll write it out once the first time. Reference angle. I think that's how you spell that, reference angle. Quadrant check, reference angle. Every time you solve a trigonometric equation, you must do in this scenario, you must do a quadrant check, you must do a reference angle. There are some trigonometric equations that don't need the quadrant check, and we'll talk about that later on. Quadrant check, reference angle. If you are in the interior, one of these special angles, one of these three, you need the quadrant check, and it's alphabetical. Quadrant check comes before reference angle in the alphabet. Q comes before R. Quadrant check comes before reference angle when you solve the equation. Quadrant check comes before reference angle when you solve the equation. All right? Quadrant check, reference angle. All right? Now, here's what I mean by that. You look at the equation, and you look at what we have is sine is equal to 1/2. So what I'm going to do, I'm going to solve this equation. Number 1, quadrant check. Quadrant check. We have sine. The fact that it's 1/2 is not important. When you're working with quadrant check, the only thing you need to know is the signum, the positive, negative. All you need to know is the positive, negative. All right? Quadrant check. Sine is positive or negative. All we need to know is whether this number is positive or negative. The fact that it is 1/2 is irrelevant for the quadrant check. The fact that it is 1/2 comes into play with the reference angle. The fact that it's 1/2 has nothing to do with quadrant check. Quadrant check just says, is that a positive number or a negative number? That's all we need to know. Quadrant check says sine is positive, right? So in what quadrant is sine a positive value? Well, sine is positive in quadrant 1, quadrant 2, all right? Sine is positive in quadrant 1, quadrant 2. Check that against the given. What are we given here? We're given, we only want to solve from pi over 2 to pi. We only want to solve from pi over 2 to pi. So, yes, this is the quadrant check. And every time you do the quadrant check, but it turns out because of the requirements of the problem, we do not want quadrant 1, so we'll just cross it off. All we're looking for is the quadrant 2 answer because that's what was given. If, a different problem. If you had been given 0 to pi over 2, then you would cross off quadrant 2 and you would use a quadrant 1 solution. All right? Did we see that? So, in this case, pi over 2 to pi, we're going to cross off quadrant 1. We need a quadrant 2 solution. All right? So we've got our quadrant check. Next we need to know is our reference angle. Which reference angle has sine? Sine is the y value, because we know our x, y, r definitions. Sine is the y value in the unit circle. Which reference angle has sine, has the y coordinate 1/2? That's this one. The reference angle is pi over 6. And so what I want you to write is this. T subscript r, reference. If this is theta, it's theta r, theta reference. If this is x, it's xr, x reference. This is t, this is t reference. If you're doing the same way the text is doing it, if you're writing s, then you would write s subscript r, s reference. So you would say the reference angle is, what is it? We said it was pi over 6. And now to find your solution, you put that reference angle in that quadrant. And if you know your reference angle families, you know that. Put that reference angle in that quadrant. So here's pi over 6. That's the reference. But t is the angle itself. So this implies t is 5 pi over 6 because that's the pi over 6 reference angle family in quadrant 2. So if you know what quadrants the values are positive and negative, if you know the reference angle families, and if you know this basic structure, then you can cobble together all the pieces. Early on, you're going to want to have all this written out. You're going to want to have maybe this written out. And you might want to have even, good Lord, you might even want to have the reference angle families written out. Eventually, the goal needs to be you do enough of these that you don't need to have all this material in front of you. You have it mentally. The only difference between what you guys are going to be doing if you have it written out and what I'm going to be doing without it written out, the only difference is I have it all written out, but it's mentally because I've done it so much. Not because I'm better at it, it's because I've done it more often. The only way to get good at this is to practice. Mathematics is like playing golf. I can watch Rory McIlroy play golf all day long. And man, he is good at it. And I understand what's supposed to happen. And then if I get out there and take the golf club, it doesn't quite work as well. The only way to get good at it is to actually do the problems. And if you do more and more and more of them, then you don't need to have this physically present. It's mentally, it's all in your mind. That is the goal. All right, so we'll practice several more of these. That's the process. Quadrant check, reference angle. Quadrant check is subject to the requirements. Subject to the restriction, you modify the quadrant check. All right? So here we go. Let's try another example here. I'm going to leave those here. We're going to solve. Let's do cosine t is equal to, let's do cosine t is equal to, let's do negative square root of 2 over 2. And we're going to solve from 0 to 2 pi. Now notice we're not including 2 pi, so we're going 0 to 2 pi. All right? This is very common. In fact, this is the most common. You solve within one complete revolution. All the solutions in one revolution. This is the most common. All right? So, this is one of these special angles, one of these three. And we do quadrant check. And we do reference angle. So quadrant check, what do we look for quadrant check? The radical 2 over 2 is irrelevant for the quadrant check. We don't care about the radical 2 over 2. For quadrant check, all we care about is the negative part. In what quadrants is cosine negative? That's why I tried to beat that into your DNA the last chapter. In what quadrant is cosine negative? Well, cosine's positive in 1 and 4, so it's negative in 2 and 3. Do we see that? We want cosine to be negative. It's positive in 1 and 4, so it's negative in 2 and 3. So our quadrants are quadrant 2, quadrant 3. Does that answer the muster here of our restriction? The restriction is yes, we're good to go. We're doing one complete revolution, so we do want the quadrant 2, we do want the quadrant 3. This problem is going to have two solutions. It's going to have a quadrant 2 solution and a quadrant 3 solution. All right? We got the quadrant check. Now, here's the piece. As soon as you do the quadrant check, you ignore the negative sign. You may now, this negative sign has done its part for king and country, and it goes off to retire in the wonderful little home. The negative is done its part. You may now ignore the negative because the negative is only used to work with the quadrant check. So ignoring the negative, now we need to choose the reference angle that has cosine is radical 2 over 2. Well, you do this often enough. The only time radical 2 shows up is pi over 4. I mean, that's the only time it ever shows up. Pi over 4 shows up at radical 2 over 2. So radical 2 over 2, that's pi over 4 is the reference angle. So I'm going to write T subscript reference is pi over 4. All right? And so now what we do is take that reference angle, knowledge of our reference angle families, and put it in quadrant 2, quadrant 3. The reference angle families for pi over 4, there is a quadrant 3 solution, quadrant 2, and a quadrant 3 solution. Remember, they're the odd, 1, 3, 5, 7. Remember this, 1, 3, 5, 7, 1, 3, 5, 7. So if this is pi over 4, that angle, right, this angle T is 3 pi over 4. So in quadrant 2, I'll make a better picture than that. It's okay, make a big picture here. If this is pi over 4, because this is T reference, this angle, 1, 3, 5, 7, this is 3. This is 3 pi over 4. That is my quadrant 2 solution. So I have T is equal to 3 pi over 4. And it's sufficient. Well, we can just list them twice. And what's the other one? The other one down here, if this is pi over 4, 1, 3, 5, 7. So this is 5 pi over 4. And there we have it. All right? All right? Now, you could practice that as many times as you like, and there will be several problems you can work on. Let's play tangent. And the one especially I want to look at is the one that has, let's do 1 over square root of 3. Now this is a little trickier because tangent, see, each of these values, the x-coordinate is cosine, the y-coordinate is sine. Tangent is not actually listed here. This is the trickier bit. So I want to solve tangent, and we want to solve this in, let's go, suppose we want to solve in, let's go from 3 pi over 2 to 2 pi. So that's the only thing we're going to solve in here, right? So, quadrant check. Quadrant check. Quadrant check is ignore the number, just use the signum, just use the negative. Where is tangent negative? Tangent's negative in positive in 1 and 3. Tangent's negative in quadrant 2, quadrant 4. Except, now we have to check that to see if it answers muster here. The restriction is only we want quadrant 4, right? This is quadrant 4. So this restriction says we do not want that solution. All right? All right, so now reference angle. All right, so here's the piece. Tangent involves radical 3. Tangent is sine over cosine. So we know it's going to be either this piece, because that involves radical 3, or it's going to be this piece. That involves radical 3. Sine over cosine is tangent. This is the y-coordinate over the x-coordinate. Sine over cosine. If we did this sine over this cosine, look what would happen. You would have radical 3 over 2 over 1/2. This radical 3 would be in the numerator. Do we want radical 3 in the numerator? No, we do not want radical 3 in the numerator, so we do not choose this. Let's check this one. Sine over cosine. Is radical 3 in the denominator? Yes, radical 3 is in the denominator. We're going to multiply by the reciprocal. Radical 3 is in denominator. That's what we want. So this is the reference angle we want. We want pi over 6. Now that's a little bit trickier, and that's why I did tangent separately. Again, if we want tangent to be pi over 6 for the reference angle, tangent is sine divided by cosine. We know it's either this one or this one. All right? If it's pi over 3, then we would use root 3 over 2, sine over cosine. And then when you would simplify that, do you see how radical 3 is in the numerator of that fraction? We do not want radical 3 in the numerator of our fraction, so we do not want that fraction. Over here, this is sine is the y-coordinate over cosine is the x-coordinate. And radical 3 is in the denominator of that fraction. We do want radical 3 in the denominator of our fraction. That is the correct choice. Reference angle is pi over 6. And then you take pi over 6, put it in quadrant 4, and you're off to the races. Knowing your reference angle families as you do, you know that if this is pi over 6, that this angle is 11. So this implies t is 11 pi over 6 because you know your reference angle families. And if you don't know your reference angle families, you're going to review them until you do know them. So I'll give you several of those to practice on, and that's the structure of solving these basic trigonometric equations. I'm going to keep you guys in the shallow end of the pool. In fact, what I'm going to do is rather than assign them from the text, there will be a few in the text I'll assign, but I might actually draw up some extra problems on your own to solve. So I'm going to have you solve some of those problems in the text, and that's the process. And it is really important that this becomes really a secure, solid part of your skill set.